Okay, so my name is Chris Exley. I'm from Keele University in the United Kingdom. Some of you may know me. Generally, people know me because of a metal called aluminium, or aluminum to some of you, which has been my subject for 35 years now. But in that 35 years, another element, another molecule has played probably an equal role in furthering my understanding of the metal aluminium, and that molecule is the one I want to talk about today. So if I'm going to disappoint you, there's going to be no images of brain slices. There's going to be very, very little to do with human toxicology. It's going to be a little bit of an odyssey, because some of you will know that one of the things I often tell people to do who might have some concerns about their exposure to aluminium is I might tell them to drink a silicon-rich mineral water. And so this lecture is going to tell you why, and to try to demonstrate actually that it's been based on, as I said, approximately 35 years of science, not just a whim of some sort. Okay, so I use the word detox there just because that's in the title of the conference. I consider silicic acid a philosophy more than a detox mechanism, a philosophy for life. I drink a silicon-rich mineral water every day of my life, except for when I'm on tour, like now, when I can't get hold of one. But generally, it's a philosophy for your protection against the possible toxicity of aluminium. So I recently put together, it wasn't really a review, it was an opinion piece all about silicic acid, in which what I wanted to do was to make the case that in the great hierarchy of molecules on the Earth, that after water, silicic acid is probably the most important. I'm only going to talk about a small part of that today, and that's silicic acid's role in keeping aluminium out of living things, as highlighted here in the red. But the rest is also interesting, I believe, and some of it has very significant implications for things like climate change. One of the reviewers of the paper took umbrage with my use of the word omniscient. And they suggested that the readers would not understand this word. I, of course, objected to that, saying that the readers would understand the word, although I may not be using it, absolutely correctly, because a molecule really probably cannot be all-knowing. But I wanted to find something which encompassed what I believe was the importance of this molecule to life on Earth. So I kept it in there. And I started to think, omniscient. Who else or what else have I come across in my shortish life that is or might have been described as omniscient? And probably many of you out there are immediately thinking of God, and I forgot about God, I'm afraid. But I did think about, gone the wrong way, I did think about this character. You know who he is? It's the Wizard of Oz. The Wizard of Oz talking to Dorothy. Of course, Dorothy went to find the Wizard of Oz. Most of you must know this story. We can sing the song to it if you like. About going to, because she wanted to get back home to Kansas, and there was an omniscient being called the Wizard of Oz who knew everything and could make everything happen. But, of course, those of you who know the story, I think most of you will know this story, will also know that that was fake news. The Wizard of Oz was just a little man behind a big microphone. Where have we seen that before? What I want to sort of tell you is that silicic acid is not fake news. So how does silicic acid keep aluminium out of living things? This year is the 30th anniversary of my first publication, and my first and only publication in Nature, in which my PhD research showed that you could protect against the toxicity of aluminium in fish simply by putting silicon into the system, or indeed soluble silicon or silicic acid. And just briefly shown here in the graph that we have, number 5 here shows 200 micrograms per litre aluminium, the amount that's allowed in your drinking water, at pH 5, killed salmon, all of them, within about 48 hours. But the same amount of aluminium in the presence of an excess of silicic acid completely protected against the acute toxicity of aluminium. And again, if I have time for a small digression, this is the culmination. Actually, this happened these data came in the last weeks of my 3-year PhD. It was getting close. And I'd spent an awful lot of time killing a lot of fish, which I really didn't like. I didn't like it. I was a fisherman. I'd gone up to Stirling in Scotland to do my degree because that's how I could go fishing every day. And one of the things I really disliked was my treatment, my experimental setup was in an enclosed temperature-controlled room with one of these really big doors that has a sort of airlock on it. And I can still remember now going in late at night or early one morning to see what had happened to the fish. And I knew when they'd all died because there was this awful, horrible, sweet smell in the air. And my poor salmon were floating about in the tank. So that wonderful moment, that epiphany, when I opened that door on one particular day, expecting to smell the horrible, sweet smell, and no smell at all. And my fish were happy, and they'd been protected by silicic acid. So how can this small molecule, a silicon atom surrounded by 4 hydroxyl groups, how can that do that? The closest molecule to this is probably water. And indeed, wherever water goes, silicic acid follows. So how is it possible? This molecule is neutral, so no charge. It has no organic chemistry at all. It has almost no inorganic chemistry that was known. When it reaches its saturation, which is 2 millimoles per litre, it will precipitate to form silica. Silica is the sand on your beach and other places. There is a reaction between silicic acid and the element molybdenum, which is used in the colorimetric test for measuring silicic acid. But this is under very rarefied conditions of low pH. So apart from that, we're talking about something that essentially has no chemistry. So how can that protect against the toxicity of aluminium in fish? And again, there are not a lot of young people here at this conference, which disappoints me. But if they were here, I would be saying to them, when you start off in science, you have to spend weeks, months, sometimes years, doing incredibly boring and dreary experiments over and over and over again. And that's what I did, in this case as a young postdoc, preparing solutions of aluminium silicon at different pHs, aging them on stirrers for weeks and weeks and weeks, and then having to filter them through membrane filters to see how the presence of silicic acid altered aluminium chemistry, altered aluminium precipitation. And that's what this was all about. And literally years later, and many, many, many filtrations later, we came up with, well, one of the curves that I'm only going to show you one that we came up with looks like this. Now what you're seeing here is a classic aluminium hydroxide solubility curve. So the aluminium comes out of solution, its minimum solubility is around pH 6.5. Another curve was also there in those solutions which contain silicic acid as well. That curve had a minimum solubility at a lower, a more acidic pH. And you also notice that this is a scale here of size, essentially. So these particles here are much larger than these particles. So in the presence of silicic acid, we have something which looks like it causes aluminium hydroxide to precipitate at a lower pH, and it reduces the rate at which the particles form aggregates. And that was essentially our first indication that something called a hydroxyalumosilicate was forming in these solutions, and that could be responsible for protecting against acute aluminium toxicity in fish. Now, I'm cognizant right now that this is the first talk after lunch. I know how I normally feel in the first talk after lunch, and my eyes would normally already be going. And you're thinking, Christ, Chris is going to talk about chemistry. We're not going to talk much more in any more detail than that about chemistry. But I need you just to see now where we went with this story. Because next time somebody asks the question, you know, this silicon-rich mineral water rubbish, what's it based on? Well, you will know what it's based on, and I will let anybody who wants the slides here have it, so you've got the full history of it. So where do we go next with this? It actually took a little while longer to make the next breakthrough in this area. And you know, it's another one of those situations where a PhD student, this time Fred Doucet, a Belgian PhD student working with me, had to do some really quite rigorous work, but incredibly boring work. He was preparing really large volumes of aluminium and silicon solutions at different pHs and aging them for weeks and weeks at a time. Now, you have to, what we needed to do, we wanted to collect the precipitates. We wanted to do some analysis on them, solid-state NMR in particular, to allow us to actually get an idea of what those precipitates were made from, what was the composition of them. To do that, you needed hundreds of milligrams of precipitate. One of the issues with silicic acid is, silicic acid, once you get to 2 millimolar, as the concentration, which is 56 milligrams per liter, it starts, as I told you, to condense with itself and form, essentially, in the first instance, polymeric silica species, and those polymeric silica species go on to form silica. Now, that's a completely different chemistry. That's actually eventually the chemistry of cement, which you've all probably heard of, but it's totally different chemistry. So we have to keep the silicic acid concentration in any solution we work with aluminium below 2 millimolar, otherwise we're dealing with another chemistry. And so to then get milligrams of material, you literally have to make tens of liters of solutions to filter them. And actually you then have to filter them through a very small 250 ml polycarbonate filtration vessel to make sure there's no contamination issues. So this, again, was a gargantuan effort by Fred Doucet, but it was worth it because it changed everything. And when we did the NMR, we were expecting at the time to find just one type of hydroxyalumosilicate, the interaction of silicic acid with aluminium, one type. But when we did the NMR, we found two distinct types which were very much dependent upon this silicon to aluminium ratio in the preparative solution. So where, for example, aluminium was in excess of silicon, we got something with a distinct NMR signature here for silicon, here for aluminium, which we called ATSA. This curve here shows that all the silicon in all the aluminium in ATSA is in what we call an octahedral coordination. It has 6 ligands around it. But as the silicon to aluminium ratio increases, we see something different, a change in the silicon NMR and a very distinct change in the aluminium NMR, showing 2 distinct forms of aluminium, one a tetrahedral form and one an octahedral form, and actually in relatively equal amounts. And when we then do some stoichiometric analysis, we find that HASA formed when aluminium was in excess has a silicon to aluminium ratio of 0.5 in the precipitate. But in HASB, when silicon is in excess, we get a silicon to aluminium ratio of 1. And these are very discrete. So we know that these are very discrete and individual forms of HAS with these very, very specific ratios of those elements. And this is just a cartoon trying to show potentially what might be going on. And again, I can't spend too much time on this, but the really fascinating thing about this is we ask the question, okay, we form HASA, and it forms from the reaction of silicic acid, not with the free metal Al3+, but with the first product of the hydrolysis of Al3+, which is an aluminium hydroxide dimer. And it immediately condenses across OH groups on that dimer. So it's almost a surface reaction. Silicic acid, neutral molecule, does a competitive condensation on an aluminium hydroxide surface. So it's really unique chemistry. So unique that we are all the product of it, by the way. But that is what's so fascinating, interesting about it. The next point was, well, how do you make HASB? And we conjectured that that's a second silicic acid reacting with two further OH groups on that aluminium hydroxide template. But it's difficult to see here, but what was fascinating, and I showed in the previous AMR slide, is that in HASB, one of the aluminium atoms, because there are two in it, one of them shifts from being Al, or octahedrally coordinated, Al6, to Al4, tetrahedrally coordinated, and it's what's called a dehydroxylation reaction. It loses water, loses hydroxides, and alters its geometry. Normally, that can only be achieved by really quite rigorous heating or something of that sort. But this was happening at room temperature, being driven by the silicic acid content. Really fascinating chemistry. Well, to me, of course. You can use methods to actually show that these two forms of hydroxyaluminum silicate look different in solution. And we can use AFM, atomic force microscopy, to show that HASB is sort of spheroidal in shape, and HASA forms more rectangular structures. So we know we've got these quite beautiful and different structures. We then were able to go on and do some what I call somewhat unconventional, and I say unconventional because most of the critics of my paper didn't like it, and I really had to fight for this, to produce a solubility product for this reaction of surface, essentially reaction of silicic acid with an aluminium hydroxide surface. And we produced a solubility product, and a solubility product which actually explains the solubility of aluminium in natural environments. So it's beautiful, and it works. I'm very proud, again, of a PhD student, Celine Schneider, who did that work. We've followed up this sort of work asking questions like, well, what happens about other elements that you will find in the natural environment, like phosphates and fluorides? Do they interact or interfere with these reactions? And again, just out of interest this is, but we were able to produce hydroxyaluminum silicates that were fluorinated, had fluorines on them. And other than the sort of academic interest that that gave for us, and this is fluorine NMR just showing that, it also gave us another clue as to the mechanism of formation of HAS A and B, because we were able to identify an actual transition state. And this transition state here has a silicon to aluminium ratio of 1, so it should be HASB. But both of the aluminiums are still in octahedral geometry, and that's because the fluoride comes on, stabilizes the intermediate state, and then the fluoride gets, well, the silicic acid outcompetes it, forces it off, we get a dehydroxylation, and we get HASB. And this is just a quick thing to show that once we started to use another set of techniques, we've also looked like we'd found evidence that the aluminium in HSB that shifts from 6 coordinate to 6 coordinate to 4 actually goes through something called aluminium 5, which again, for our purposes was very, very, very interesting. He then wanted to do something, and this is one of those experiments where, in this case, was a French engineering student, has to do lots and lots and lots of solutions, collecting them, stirring them over long periods of time. He asked the question, if we collect the precipitates as early as possible in the precipitation process, under different sets of solution conditions, can we use that to prove that the first precipitate formed in these reactions is HASA, and that is the precursor to HSB? Because at this point, we haven't proven that. It's all been down to structural analysis of precipitates that have been formed. And to go through it relatively quickly, in this type of a situation, we would predict where equal amounts of aluminium and silicic acid, we would predict HASA to be the final product, and it is. And when we look after 12 hours, it's also HASA. Again, the prediction for this is to get mainly HASA. And when we look after just 12 hours, the silicon to aluminium ratio is about a half. So it's HASA, as we predict. Now we're getting to a stage where the silicic acid is in excess of the aluminium, and we start to think we should form HASB under these conditions. So we have a look at what we've got, and we've got in the final product after 300 hours, a silicon to aluminium ratio now approaching 0.84, that says, so approaching 1. So we're getting HASB formed. After 12 hours, it's still HASA here. So it's looking interesting. We go for one step further, where we've got a significant excess of silicic acid to aluminium. We predict that the final product will be HASB, and it is. But look, we managed to collect precipitate after just half an hour of the reaction taking place, and do stoichiometric analysis of it, and get enough of it to do that, and the silicon to aluminium ratio is a half. It's still HASA. So the first precipitate formed is HASA. So these things form. Aluminium hydroxide reacts with silicic acid to form HASA. HASA reacts with more silicic acid to form HSB, and we get this beautiful dehydroxylation reaction to produce incredibly stable complexes, which actually, once you've filtered them and collected them, do not dissolve in concentrated nitric acid. So I'm going to go through the summary. These slides, anybody wants them, just ask, email me, you can have, and you read the summary. So what we've got at this stage then is me trying to think, okay, how far have we got? What do we know? And how could we actually understand what's happening in the very early stages? Now clearly, there's no method at the bench where we can look at the reaction of the first aluminium hydroxide formed with a silicic acid molecule, way beyond anything that's available at the bench. So I contact my great friend Xavi Lopez in San Sebastian in Spain, and can we do this computationally? And I honestly feel, I can just about work a computer. But some of my very, very best work is right here because of my postdoc James Beardmore, Xavi Lopez, Johnny Musica. We were able to use their methods with our knowledge and assumptions to produce what I believe is definitive evidence that what we believe to be the case, the mechanism of formation of hydroxyl in the silicate, is exactly as we say it is. And again, just a summary of it there, the aluminium hydroxide reacts with silicic acid to form HASA, which reacts with further amount of silicic acid to form HSB. What was really exciting in this computational thing stuff was that the computer program did it. In other words, when we increased the silicic acid content, the molecule HSA broke up, threw off water, took on another silicic acid, and reformed into exactly what we expected it to do. I mean, this was unbelievable stuff. A wonderful moment, for me at least. And particularly for someone who might be a little bit critical of computational chemistry and computational studies, perhaps no longer. So it was a great moment, great moment. And even better because, my prediction that I did as a celebration of 200 years of Darwin's birth and 150 years of the origin of species, Tibbs asked me to write something about aluminium and silicon. And my predictions there were that aluminium is non-essential because it's never been available for any biological or part of biochemical evolution because of silicic acid. And that is entirely true today. But of course, what happened was, essentially man happened. And even more than man was what I call the aluminium age, the advent of the aluminium age. Because less than 120 years ago, we worked out how to take these inert aluminium silicate ores and make aluminium metal. And from aluminium metal, make aluminium salts. And from aluminium salts, the aluminium age that we live in today. A wonderful age. It heralded the modernity we see today. We could not have life we have it today without aluminium. So it's been a fantastic boost to us. It's been marvelous. The aluminium age. I went to school, the Iron Age, the Copper Age, the Bronze Age, the last 120 years, the aluminium age. But of course, you would expect that with any age, or anything that's newly introduced into life and living things, including humans, would be demonstrated to be safe to use. And that's where the problem arises, because that has never been the case with aluminium and isn't the case today. So a lot of our research has been all about aluminium, and it's also been about, can we protect against the possible toxicities of aluminium? And again, I'm just going to go very briefly here. One of the things that we were able to do was there is a link, inverted commas, between human exposure to aluminium and Alzheimer's disease. If you asked me that question over dinner last night, I would have told you that it's not just a link, it's almost inevitable. Once the brain aluminium content reaches a certain level, it will contribute towards Alzheimer's disease. Inevitable. So, can we do something about that? Well, if we get individuals with Alzheimer's disease to drink a silicon-rich mineral water, which we have shown in our research facilitates the excretion of aluminium from your body, maybe we can lower the amount of aluminium in their body, maybe we can help them. So the first thing to prove, of course, was that by drinking a silicon-rich mineral water every day, and in this case the clinical trial was for 12 weeks, listen, you would not believe the type of ethical permission you need to get somebody with Alzheimer's to drink a bottle of mineral water that they can go to the shops and buy and drink themselves. It took a year to get ethical permission to do a study like this. Oh, we're asking them to drink a litre of water. That could be dangerous. Yeah, okay. And we had to prove that it wasn't. And we did, of course. And we did the study. In particular, we showed that what we call the body burden of aluminium was reduced in the individuals who drank this. Only 12 people in this study. We do not have money. This is a study that cost probably £50,000 in total. Really interestingly for this study, though, we were able to do some secondary outcomes which were related to the cognitive function in these individuals. So actually I think it was 15 individuals, it probably says so on there. Let's go to the next slide where you can read it. Yeah. We were not only able to show that we could lower the amount of aluminium in their body, but 20% of those people, within only 12 weeks of drinking a silicon-rich mineral water, their cognitive function improved by a clinically relevant amount using the ADAS-Cog score. Now, this has never been achieved for neither any of the 4 drugs we have today to give for people with Alzheimer's disease, all of which are completely useless and just fund the pharmaceutical industry, nor indeed any of the failed drugs have ever achieved this. And yet, how many years later am I still trying to get funding to do a study like this? But it remains exciting, and it remains something that anybody, and I get contacts once or several times every week about Alzheimer's. I say, look, I'm never going to get the money probably to do this huge clinical trial that we need, so just start drinking a silicon-rich mineral water and do it every day. And protect yourself just in case I am right and not the crazy quack that the internet says I am. We've just finished another piece on multiple sclerosis. We had suspected from some time ago that aluminium was involved in multiple sclerosis, and recently, of course, you may have seen our research showing aluminium in brain tissue in people with multiple sclerosis. So this study was started before that work, but again, the idea was, can we, in the first instance, show that regular drinking of a silicon-rich mineral water lowers the body burden of aluminium in individuals with multiple sclerosis? And we were able to do that. We were not able, because of ethical considerations, to do any clinical outcomes on these individuals. However, I've got one small, I'm looking at my chairman over there, because I always feel like I must be going over time, and he hasn't made any strange noises yet. I was called by a local neurologist in Staffordshire one day on the telephone. And this person said, Professor Exley, have you recently carried out some sort of clinical trial on multiple sclerosis? And I said, yes, we did. It finished about a year ago. I explained it to him. I said, I can send you the details if you like. And I said, well, why do you ask? He said, well, because one of my multiple sclerosis patients, inverted commas, was part of that trial and no longer has multiple sclerosis, and told me that since the trial finished, they continued to buy the silicon-rich mineral water from the supermarket and continued to drink it, and they no longer have multiple sclerosis. Interestingly enough, I thought this person was going to be a wonderful contact. And then they disappeared, literally. I couldn't contact them, they didn't answer any emails. It's almost as if something happened, inverted commas, not necessarily to them, but they'd said the wrong thing, who knows. But anyway, that was a lovely piece of anecdotal evidence. And as the next slide tells us, myriad anecdotes do not make a clinical trial, unfortunately. But I am contacted. Today, before I came to give my talk, I sent 2 or 3 emails out to people who've just asked, Chris, what can I do about this? My son's been impacted by Gardasil. My father-in-law's just been told he's got Alzheimer's disease. I've got the early stages of MS. And I am not a clinician, I'm a biologist. I don't give clinical advice. So I simply say to everyone, as I would say to you now, if aluminium is involved in the symptoms, in the disease that you were experiencing, then if you really commit to drinking a silicon-rich mineral water every day, about 1 litre, which is not a lot of water, it might sound a lot, but it's not a lot, and it doesn't have to be your only source of water, but 1 litre of a silicon-rich mineral water every day, and do it for the rest of your life, when you can. I haven't done it today, I'm sorry about that, but where it's possible, it may help. And of course, I get a lot of replies weeks and months and even years later, including from someone with Alzheimer's disease who no longer has Alzheimer's disease, and many parents with children with autism whose children are suddenly talking and making incredible improvements. Now, I only get the positive replies, I believe. No one emails me to say, it didn't work, you're useless. I don't get that email. But I suspect they're out there. But from those myriad anecdotes, it gives me hope. I suppose my main hope would always be that aluminium is benign. Because if aluminium is benign, and I am totally wrong, the world is going to be a lot better for it. But if I am even slightly right, then our complacency today with respect to the toxicity of aluminium and our government's complacency is not only a time bomb that may go off, this time bomb has gone off. And we are suffering the worst chronic disease in the developed world ever today, and it will be worse tomorrow. And aluminium is almost certainly playing a part. So silicon-rich mineral waters, which the government are never going to tell you to drink because that would be an admission that aluminium is bad for you. But we can do that. And I suggest that where we can, we do. So thank you for your attention.
Thank you very much for a fascinating inorganic chemistry lesson. Yeah. Now it's time for questions.
Which has to be a first.
Yes.
what should be the optimum level of silic acid in the mineral water to obtain good results?
Yeah, so it's a great question. What constitutes a silicon-rich mineral water? And the truth is, we can only go on our experience of the ones we've used. We have not been able, because of funding, to do that as a hypothesis and do a testing of that. But what we found is that any mineral water where the content of, and this is where it becomes confusing, the water industry has always called soluble silicon or silicic acid, they've called it silica. I don't know why. But it's, so written on the bottle is nearly always silica, or the German or French or whatever it is version of that word. But if it says 30 ppm, 30 milligrams per litre or higher, which for example in Europe would be equivalent to something like Volvic, then we know that works. We have tried waters that are down at the less than 10 milligrams per litre, and we see no benefit from those. So related to that, is there a dose response? So if I have a silicon-rich mineral water that's 50 or 60 parts per million, will that be better? I don't honestly know. Intuitively, I believe it will be. And the reason I believe that is, let's imagine, how does it work? So you've seen this stuff on hydroxyalumosilicates. So you know that silicon, as silicic acid, is going into your body and forming a hydroxyalumosilicate. That means it's got to find not aluminium, it's got to find aluminium hydroxide. Now, we've got other research, and actually another computational study by me, for heaven's sake, which shows that aluminium hydroxide does form in the blood in small amounts. So you drink silicic acid, or you drink water rich in silicic acid. The silicic acid follows the water through your gut, and you immediately get, I'm getting some feedback now, you immediately get a very high concentration of silicic acid in the blood, like a pulse. That high concentration is sufficient to both form a hydroxyalumosilicate and keep it small enough so that it can be filtered by the kidney and into the urine. So a higher content of silicic acid might be more effective in doing that, and I would like to be able to test that if we had the funding to do so.
Thank you so much. Two questions. If you say it's excreted into the kidneys straight away, wouldn't need a lot of funding to do some urine testing for aluminium, would it? And
all these studies are urine tests for aluminium.
yeah.
So in the Alzheimer's study, in the multiple sclerosis study, and in fact we've done many others, our way of estimating body burden of aluminium is urinary excretion of aluminium.
Sorry, I should have asked more specifically. If you were wondering about which the ideal concentration was, whether it was 30 or 60 or whatever, that should be easy to determine in a sort of given patient who's not losing a lot through one urine per day. You know, well, next state would be relatively the same.
The concept is exactly as you've said, can be done. Obviously, you know, I can't do that study on myself without ethical permission. So you have to go through, and if you want to do it on several people, and then you want to do it over different concentrations, and then it's a study.
Yeah.
We don't have this funding. I would love to do that, simply because, you know, this is my chemistry. I want to show that this chemistry will benefit mankind. So yes, you're absolutely right. The studies are all possible. If you've got a spare few £100,000, I've got a link to a donations page.
Next question is about saving money rather than spending it, if you don't mind. I've recently been walking through British supermarkets again, trying to find some mineral water in glass bottles. I completely failed. It's not that too much different in Europe, although there's a few glass bottles left. Now, if I get this silica-rich water, I also get, unfortunately, a phthalate-rich water. So is there any alternative, such as, I don't know, is it a concentrate or some just horsetail tea, or have you tried anything else which prevents us from getting all these plastic toxins in?
This is a beautiful question, because, and I seriously would say that if I had $1 or £1 in our country, for every time someone has said to me, well, Chris, what about all these silicon supplements you can buy? Can I use one of those, or can I add it and it'll dissolve? It's silica. They're all silica. It is, and even a gentleman I know called Dennis Krauss has made something called Silicade, which he makes in his garage and tells people to drink. You know, silicic acid, I showed a slide right at the beginning of my talk, the silicic acid cycle. It is the product of the dissolution of mountains. That's where it comes from. Yes, I can make it in the lab, but it's extremely complex to make it, and you can only make it in certain ways, up to certain concentrations. And also, I wouldn't drink silicic acid made in my lab. It could kill me. I've got no control over its safety or anything of that sort. So none of the silicon supplements, and we have tested literally hundreds of them, into the gut. We've done, with individuals, we've done tests where we have artificial stomachs to see whether we can get silicic acid out of them. None of them give anywhere near the amount of silicic acid that will, as we just talked about, produce that pulse of high content of silicic acid in the blood. I wish there was. I'm even trying to raise funding for something that I call the silicic acid pill, because we also work on silica deposition in plants like horsetail, my wonderful favorite plant from my garden. Horsetail is full of silica. The question is, how does it take silicic acid and make silica? And in the meantime, it's able to do that through intermediates, which if we can do something where we are able to sort of stabilize one of the intermediate stages, we might have a silicic acid pill. But that's going to be tough chemistry.
So much.
Chris, just getting back to nature. In the times of our ancestors, they, if you go down to the, I gather that where the waves break onto the sand at the beaches, you would get an increase in silica in the water. And when our ancestors, the old people, when people went down to
No, you won't.
Won't.
Because sand.
Yeah, but that,
Sand, if, you know,
Because
thermodynamically,
in the
if you
olden
take
days-
a grain of sand, thermodynamically,
Yeah.
you take a grain of sand and pop it into a litre of distilled water, thermodynamically it will form silicic acid in seconds. But actually you have to wait 100,000 years. So this is the problem. Once silica is formed, it is essentially inert. It cannot give silicic acid. So it's only silica, which is not this story. This is the story of silicic acid.
I was just wondering, because our ancestors always, if somebody goes down to the beach, they say, bring me some seawater, it's so healthy.
Yeah, well, I love to swim in the sea. I never swim in a swimming pool, and I love that, and I'm of the belief that that's good for me, but it's got nothing to do with silicic acid.
Seawater would have been cheaper.
Okay.
Thank you, Chris. Are there such a thing as blue zones for silicon-rich water?
Is it Dennis Krauss that's used that term, blue zone? I'm not sure. I've seen this word. So there's some intriguing geography out there. So for example, where in the developed world is the lowest incidence of Alzheimer's disease? Anyone from Japan here? Japan has the lowest incidence of Alzheimer's disease in the developed world, and it has the highest content of silicic acid in its natural waters because of the very high volcanic activity on that island. Very quickly, an anecdotal story, well, a story in relation to that. A French group for years looked at the relationship between incidence of Alzheimer's disease and aluminium in water, drinking water. And you get a sort of positive relationship, but it's weak. It's about 1.5 odds ratio. If you instead look at the content of silicic acid in the water versus incidence of Alzheimer's disease, you get a perfect inverse relationship. You are 5 times less likely to get Alzheimer's disease if you live in an area where the silicon or silicic acid content of the tap water is high.
And this is entirely self-serving, but does it contribute to your skin looking so wonderful?
Is that a shut-up line?
Is it just me?
I better not answer that question, but thank you. Thank you very much.
You didn't answer the question.
I said I better not, I thought.
Oh.
I don't think it's, well, my answer would probably not be for everyone's ears. If you want to ask me later, I'll tell you. Is that a reverse chat-up line?
Thank you very much.